All right, so what we're going to do today is we're going to continue with all of the work we've been doing on generating functions. So the whole point is to try to find which version is going to lead to the best algebra. And so we talked last time about sums of random variables. We've talked numerous times about how the density of a sum of independent random variables is given by a convolution. The density being given by a convolution tells us that we want to create objects that are nice with respect to convolutions. And generating functions are such objects. The generating function of A star B is the generating function of A times the generating function of B. It converts convolution to regular multiplication, which is much nicer. And then we can prove a lot of different properties. All right, so as an example, let's look at sums of Poisson random variables. Now we have a wonderful theorem in the discrete case. So in the discrete case, we have the following theorem. XY discrete random variables take on non-negative integer values. Then the generating function of x equals the generating function of y for s less than delta, delta greater than 0, means x and y have the same distribution. So this is a wonderful fact. Two random variables are the same when they're discrete, taking on non-negative integer values, if and only if their generating functions are the same. So this provides a test of whether or not two things are the same. What do you think is going to be the most important function, or the most important random variable, the most important generating function later in the semester? The normal. Is the normal discrete, taking on integer values? And that's where the trouble is going to come. This theorem is not true in the continuous case. You can have two distinct continuous random variables with the same generating functions that are not the same. This is why real analysis is such a, oh, I got my kids here. This is why real analysis is a long class, all right? And there's a lot of technicalities. Complex analysis is a much nicer class in that you don't have any of these issues. I don't have to worry about watching my language because you don't have bad things like that happening. Let's say now x is Poisson with parameter 5, y is Poisson with parameter 7. And let's look at x plus y. Okay? So the first thing is we need to know what is the generating function of a Poisson random variable. All right, well, this is a general calculation. So let's say w is Poisson with parameter lambda. So we need to know what is the definition of the generating function. It's the expected value of s to the w. I'm doing this right? Yes. Right? And so for us, this is going to be the sum, n goes from 0 to infinity, s to the n, times the probability w equals n. So this is just the definition of the generating function. All right, so now let's just do some algebra. N goes from 0 to infinity, s to the n. The probability, since it's a Poisson, is e to the minus lambda, lambda to the n over n factorial. So when you look at this, eventually you should hear it telling you what to do. What do we want to combine?
The s and lambda.
So we want to combine the s and the lambda. So this is e to the minus lambda. Sum n goes from 0 to infinity, s lambda to the n over n factorial. And then this is going to just be e to the s lambda. Or just putting everything together, we get e to the, there's lots of different ways I'm saying. Did I choose to write it down over here? No, I just wrote do sums. All right, so we can do it two different ways. S minus 1 times lambda. We could have also written it as negative 1 minus s of lambda. I've done these calculations so many times I just wrote do Poisson. So I'm not sure which way we wanted to finish the algebra. We'll leave it like this. This is the generating function of a Poisson random variable. If lambda equals 5, I just plug in 5 here. If lambda equals 7, I just plug in 7 here. Now we go back. X was Poisson 5. Y was Poisson 7. Do you think there's anything special about 5 and 7? Now, I got my kids' ages wrong. They're 6 and 8 now. Oh, well. I probably did this example last year. Okay? So now, if we look at the generating function of x plus y of s, with them independent, that's the generating function of s, of x at s, generating function of y at s. All right, so we get e to the s minus 1 times 5. Oh, wonderful, using a 5 and an s. E to the s minus 1 times 7. Well, what do we do? Just combine them. Kayla, what's 5 plus 7? Yeah, I need you to solve that pretty quickly, Kayla. You're holding up the math lecture. What's 5 plus 7? You can get an M&M if you solve a problem right. Yep, you can come up and get your M&M. Okay? You get an M&M. Yeah. Yep, now, yes. This is the difference between marketing and math. We actually give out M&Ms. So I'll give you the next problem, Kim, okay? E to the s minus 1 times lambda with lambda equals 12. So now what can we conclude? Since the generating function is unique for a discrete non-negative integer, x plus y is Poisson 12. It has to be Poisson 12 because this is the moment generating function of a Poisson random variable with parameter 12. So to me, this is a lot easier than the algebra we did before when we looked at the convolutions, when we did the definition, and when we did the clever algebra with the binomial theorem to work things out, to massage it, to get all the algebra to work out, and then see at the end of the day it was a Poisson with parameter 12. This is much nicer. Moment generating function, bind them, done. Okay, this is the power of the of the generating functions. Moment generating function will come later. Again, the reason this works is we have this wonderful theorem. This theorem does not hold for continuous random variables. But because we can identify the generating function here, we're in great shape. Okay, any questions about the Poisson example? Okay, so we talked about continuous generating functions. So we could say x is continuous random variable, density fx, then the generating function x of s would be the integral from minus infinity to infinity of s to the x fx of x dx, which again is the expected value of s to the x. So the only thing that's changing is now instead of having a sum, I have an integral. Which would you rather have as a rule of thumb? Integral. Usually integrals are nicer. Unfortunately, for technical reasons, the integrals will be harder because we won't have theorems like this at our disposal. And so in fact, this is a good time to erase it because it's gone. All right. So let's take as an example, let's say x is exponential with parameter lambda. So this means the density function is going to be 1 over lambda e to the negative x over lambda if x is greater than or equal to 0 and 0 otherwise. So we can now calculate the generating function. So the generating function is going to be the expected value of s to the x. So it's the integral. I'm not even going to bother writing from minus infinity to infinity because I know my density is 0 until I get to 0. So I'll get s to the x e to the negative x over lambda dx. OK. So now the question becomes, how do we attack something like this? This is definitely a 1 over lambda, yes. And I checked my notes. My notes are useless. It says just do exponential. So I have no crutch either. How would we handle something like this? We have to look at the algebra and we have to find what is the way to make the algebra sing to us. Is there any value of S that would be easier to study than others? There's two values that should be a little bit easier. What's one value that's easy? 1. Because if S equals 1, good, that goes away. There's another value of S that's easy. All right, I'll give you 0. E, excellent. Why is E nice? You can combine. So what this is telling us, if S happened to be E, everything was nice. So what I'm going to do is I'm going to do a trick. I'm going to, in some sense, change variables and write S in terms of E. So S is equal to E to the log of S. And this is then the same as S to the x is E to the x log S. The hardest part to remember right now when you're doing this algebra is S is fixed. We're evaluating this integral for a fixed value of S. And so if I do that, I get the generating function is equal to the integral from 0 to infinity of 1 over lambda e. I've got a negative x over lambda and e to the log x. I'm going to write this as a negative 1 over lambda minus log of s x dx. I'm just doing algebra. I want to have a negative sign. Why do I want to have a negative sign? This is an exponential. If I have a positive sign here, this is going to diverge. So this tells me that this generating function is only going to make sense if the log of s is sufficiently small. If s is a huge number, this is going to be growing faster than this is decaying, and it's going to blow up. So we can tell here we're going to need 1 over lambda to be greater than log of s, or if we move things around, the log of s is less than 1 over lambda, so I think you get s is less than e to the 1 over lambda. If I don't have that, this integral will not make sense. But as long as that's the case, this integral makes sense. This looks a lot like an exponential random variable. The thing that prevents it from being an exponential random variable is this is supposed to be in the denominator. That's not a big deal. So again, all we're going to do now is we're going to just do algebra to try to make this easier. I could do a direct change of variables, but I already know what the integral of an exponential random variable is, so I'm going to just convert this to that form. Because if I can make this look like an exponential random variable, I'm done. So I'm going to write this as gx of s is equal to 1 over lambda, integral from 0 to infinity, e to the negative x divided by 1 over lambda minus log of s to the negative 1. So that's going to be my exponential parameter. And now I'm going to multiply and divide by the same thing. 1 over lambda minus log of s, inverse over 1 over lambda minus log of s, inverse dx. I pull this out from the numerator, and I get 1 over lambda. This part over here, it's a 1 over, so it becomes 1 over lambda minus log of s. Integral 0 to infinity e to the negative x over a times 1 over a dx, where a is 1 over lambda minus log of s inverse. This is now the integral of an exponential with parameter a. What's the integral of an exponential with parameter a? 1. So again, if you wanted to, you could have changed variables over here. You could have let u equal this times x and play your u du game if you want. That's a perfectly fine way to attack this. What I want to do is, well, I know the integral of something of the form e to the negative x over a, 1 over a. Let me just get it into that form. And then I'll identify a, and as I do the algebra, it'll fix things up over here. So the lambda times this becomes 1 over 1 minus lambda log of s, and this integral is just 1. And here is the moment generating function. So we get x is exponential lambda, then its generating function is just 1 over 1 minus lambda log of s. And if you think about this, as soon as the log of s is greater than 1 over lambda, well, when it hits 1 over lambda, this is undefined. When it becomes larger, this becomes negative. That precisely matches our condition. So we have to remember to say log of s is less than 1 over lambda, or equivalently, s is less than e to the 1 over lambda. So there are conditions, there are conditions in when we can use this. I'm not going to go through the algebra now, but if I had two exponential random variables, we could calculate what the moment generating function is of the sum. And we could see, is the sum of two exponentials an exponential? What do you think? You think it is or is not? It's not, unfortunately. It's very rare to have the same shape to have a stable distribution. Poisson is one of those examples. The reason the central limit theorem is so prevalent and important is the normal is stable. Sums of normal are normal. The Cauchy is another one. Sums of Cauchy are Cauchy. OK, any questions about how we do these calculations? So what integration class do we really need for all this stuff? Which class is it? Which calculus class are we using? Nope. Calc 2. It's now essentially Calc 2 problem after Calc 2 problem after Calc 2 problem. It's just doing integration. We're not doing differentiation. We're not doing multiple integrals. We're just doing Calc 2 problems. But now you at least have a sense of why we care about these integrals from Calc 2. These integrals will help us figure out things about probabilities. They'll help us calculate events. That's why we care about stuff like this. Okay? When we get to the moment generating function, we'll do a little bit of Calc 1. We'll do some differentiation. But right now, it's all Calc 2. OK, any questions about exponential? We're good on exponential. All right, as a nice exercise, try to do the normal. Try to do some other ones. Try to do the uniform. And just see what they're like. All right, so the next thing I want to talk about is, yes, we've got to essentially repeat all the results from before, or at least all the results that we can. So some of the properties are not going to hold. We're not going to have the generating functions uniquely determining the random variable. That's gone. But there are other properties that we'll still have. So one of the nice theorems we have is the generating function of x plus y of s is the generating function of s, generating function of y. If x and y are continuous, independent random variables. OK? So there's lots of ways to prove this. One is g of x plus y. It's going to be the expected value of s to the x plus y. What's the expected value of s to the x plus y? I'm sorry? OK. It's the expected value of s to the x, s to the y. Now what do I do? Good guess to take the log. This is one of the few times when you don't take a log when you see a product. Not a bad guess, though. Yes?
Aren't x and y independent?
X and y are independent.
Break it into two expected values.
So we can break the expected value of the product into the product of the expected values. And so you've got to prove that if x and y are independent, then s to the x and s to the y are independent. OK, so now we get the expected value of s to the x, the expected value of s to the y. You can begin to see now why it was worth having this as a definition of the generating function. I'm not writing down all the integrals. I'm just working formally. What's the expected value of s to the x? Yeah, generating function of x at s, and then the next is generating function of y at s. And if you wanted to, you could even write these in the opposite order. Why can I write those in the opposite order? I'm sorry? Yeah, multiplication is commutative. So because multiplication is commutative, I then get gy of s, gx of s. So I could use the commutativity of multiplication to write them in this order here. I could also use the commutativity of addition over here and say the generating function of x plus y is the same as the generating function of y plus x. And so it doesn't really matter where I use commutativity as long as I use commutativity. So the book goes through all the stuff in great detail. This is essentially the same as what we did in the discrete case. I don't want to spend too much class time going through it because it's the same. So we have sums of 2. Their generating function is the product. If I had more terms, what would it be? If I had, x1 plus x2 plus xn, the generating function of a sum is the product of the generating functions. So we get g x1 plus, whoa, that's a big xn of s, is the product, k goes from 1 to n, of g xk of s if independent. And this is just grouping, just using parentheses. So that's an extremely powerful technique. We've seen this time and time again. You group x2 through xn together as your second random variable, and now we just keep using the 2 result. So it's very important just to prove the case when we have 2. Okay. This also allows you to prove that that convolution of functions is commutative so long as the functions correspond to probability densities. So f star g is the same as g star f because we have this interpretation of them as sums of random variables. It turns out convolution is also commutative even if they don't come from probability distributions, but then you can't use the same argument. All right, so I'm not going to bother going through all the stuff like that. That finishes up section 19.5. And I am very glad to be done with section 19.5. I have made mistakes, some of them deliberately, some of them accidentally. Maybe snowing. Let's see. Well, I'm very impressed. Only about 3 or 4 of you turned your heads. When it was snowing yesterday in a faculty meeting, about 89, 90% of us turned our heads. Then somebody said, squirrel, squirrel. That got 100%. What mistake have I been saying when I've been talking about generating functions? I've corrected myself many times. Yes, I keep saying moment generating functions, moment generating functions, moment generating functions. So part of it could be lack of sleep. Part of it could be I'm nervous. I've got my kids here today. Really want my A game on. The sad thing is they're here one day too soon. I wish they could be here for Monday's lecture, because on Monday's lecture I might have done one of the exam problems, which the kids actually helped me create. But why do you think I want to deal with moment generating functions and not generating functions? Moments are useful. It's going to be better algebra. I don't want to deal with generating functions for this class. For probability, the generating function is not as useful as the moment generating function. The goal, the dream, is that if I give you a nice sequence of moments that uniquely determines a probability distribution. We know the sequence of moments for the normal random variables. So if I want to prove something becomes normal, I look at its generating function, or I look at its sequence of moments, I show they agree or converge to those of the normal, and therefore it must somehow converge to the normal. There are several problems with that. 2 biggest are 1, unfortunately different distributions can't have the same sequence of moments, and 2, not every random variable has a moment generating function that exists. So sometimes you can't even use the moment generating function approach. There is another version of the moment generating function called the Fourier transform or the characteristic function, which we'll talk a little bit about, which always exists. And if you have your choice between studying something that exists and studying something that does not exist, as a rule of thumb, it's better to study something that exists. Okay? So moment generating functions. All right. So we're going to define the kth-centered mean. We'll put it in the colon to mean it's a definition, to be the expected value of x to the k. So it'll be the integral from -infinity to infinity of x to the k fx of x dx. So this is the kth moment. And it's not centered. we'll have, mu k, the kth centered moment, will be the expected value of x minus mu to the k, where mu is the first moment. All right, so the generating function of x was the expected value of s to the x. The moment generating function, and I want to make sure I use the same notation. I think we use the letter t for this. Yes. Of t is going to be the expected value of e to the tx. So the first thing is there really a difference between the moment generating function and the generating function? Or is there a conversion between the two? If you know one, do you know the other? So how can I pass from the generating function to the moment generating function?
You can just set s equal to e and scale x by t.
So let s equal e to the t. And so if I evaluate this at e to the t, I get the moment generating function. What about going in the other direction? Can I get from, I should be able to. So what would I take t to be? Log s. So this is the trick we saw in the exponential. It was not a coincidence that I wanted to talk about the exponential earlier. It's all about what makes your life easiest, what minimizes the amount of algebra you have to do. Cameron? When you were in school, how did they make you add numbers? Come up over here. This is your chance to get an M&M. Okay? Yeah, so if you want an M&M, come up over here. And I'm going to show you how he had to do numbers. All right. So 358 plus 73. How did you have to do this?
I had to add the 300 to the 0, so I put 300 there.
Okay, now what did you have to do?
Add the 50 and the 7 and put them there.
And how would you write that? 1. 50 and 70.
150.
50 and 70 is 15?
No, it's 150. Wait, no, wait. 120.
120. And now what else did you have to do?
And then add the e and the 3, which is 11.
And now what did you have to do?
Add that.
Add that. Does anybody remember this from their school days? All right, so how would you add this?
So first those, the 3 and the 1, which is 4.
Uh-huh.
Then the 2 and the 1, which is 3. And then the 0 and the 1, which is 1.
And now how did you want to add 358 and 73? How did you want to do it?
So 1 here.
So 1 here.
Then 1 there.
Okay.
And then
And so 5. Now what do you get? You gotta do it quickly. We're running out of time for the M&M.
then a 3.
Then a 3 here. And now what?
And then a 3. Wait, then a 1 there.
And a 1 here.
3. And then a 4.
Okay, you can get your M&M. You can get 2 M&Ms. You can get 2 M&Ms. Okay? Which way do you prefer? This one, right? This is how, now, but Cameron's teacher was very good. She let him explain this method to the class with the carry. Fundamentally, does it really matter which way you work? But in terms of doing the algebra, one way is often significantly better. This is the lesson I want you to think about for the generating function versus the moment generating function. One of them is designed to be better for calculating quantities. And it's amazing how much better one is than another. So let's see what's going on. So the moment generating function of x is going to be the expected value of e to the tx. So this is the integral from minus infinity to infinity of e to the tx fx of x dx. And we're going to assume it converges if the absolute value of t is less than delta. I am going to argue fast and loose right now. Okay? Imagine I'm wearing my physics hat, or even better, my econ hat. Okay? How should I view e to the tx? What's a good way to view e to the tx? How would you interpret e to the tx? Not e to the t times e to the x. You could do it as e to the t to the x, but that's not going to be useful. That'll just get us back to the generating function. How would you actually compute e to the tx? How do you compute the exponential of anything? What do you use? I'm sorry? Okay, how do the computers compute it? How do you calculate the exponential of something? I'm sorry? So you could do it as the limit of a product, but we don't like dealing with products. You do it as an infinite series. So this is the same as the integral from minus infinity to infinity, the sum, n goes from 0 to infinity of, well, this should be a lowercase x at this point, of tx to the n over n factorial times fx of x dx. Still wearing our engineering econ hat, what do we do now? Pull the sum out. Are we allowed to do that? Yeah. So that has to be justified. All right, what two words are you all thinking of right now? Real analysis, okay? So you take a real analysis class, and they justify when you can interchange an integral and a sum. This is Fubini's theorem. I think, have I already given you an example in this class of where Fubini can fail? Have we done that? Okay, so Fubini sometimes fails. We are fortunate we're in a situation where Fubini doesn't fail. One way to check is if you put in absolute values, and the integral of the sum of the absolute values is finite, then you can switch orders. We switch orders. So we now have the sum, n goes from 0 to infinity, the integral minus infinity to infinity of t to the n, x to the n over n factorial fx of x dx. So we interchange the sum and the integral. What should we do now? So how should we handle the algebra? What should we do now? Yeah, pull out constants with respect to x. We can pull out the t to the n. We can pull out the x to the n factorial. So this is the same as the sum. N goes from 0 to infinity. The integral minus infinity to infinity, x to the n, fx of x dx. And I'll put the tn over n factorial over here. Okay? What's this integral equal to? What's that integral? Yeah, the nth moment. So this is just the sum, n goes from 0 to infinity, of mu n prime t to the n over n factorial. So if you look at the Taylor series expansion of the moment generating function, assuming it exists, it's a dream come true. Its coefficients are the moments. Right? Not only are the coefficients the moments, you've got this n factorial down here. So it's not quite the coefficients of the moments, it's even better. It's coefficients of the moments divided by n factorial. If I take n derivatives, I get an n factorial coming down from here, right? And then when I plug in t equals 0, the only term that survives is the nth term. The n factorials cancel, and I get exactly the nth moment. So what we get as a theorem, if we take the nth derivative of the moment generating function of x and then evaluate it at t equals 0, that's the nth moment. So it's really easy to calculate moments if you know the moment generating function. The moment generating function bundles everything together. Okay? So as an example, let's go back, and we did the exponential function earlier. Well, we'll keep all this. We'll come down over here. So we calculated earlier that if x was exponential lambda, its moment generating function, I'm sorry, its generating function, we did its generating function, right, was 1 over 1 minus lambda log s. We did this calculation before. I want the moment generating function. I should technically do the integration all over again, or I can note, hey, there's a really nice relation. If I take s equals e to the t, I can get the moment generating function. All right, let's take s equals e to the t. This is an example. And so now we get the moment generating function of x at t is the generating function at e to the t. Right? And so hopefully this will all work out. And we get 1 over 1 minus lambda t. So now if we want to calculate the mean, if we want to calculate the second moment, we just start taking derivatives. So I'm going to show you two different ways to calculate the mean in the second moment. The first is derivatives. So mx prime of t, so I take the derivative. This is 1 minus lambda t inverse. A negative 1 comes down, this to the negative 2. Then I have a negative lambda coming from this, the negative and the negative reinforce. And I get lambda 1 minus lambda t to the negative 2. And then when I put in t equals 0, we get lambda, which is the mean, the expected value of x. Probably other ways of writing mean, but that should be more than enough. All right, let's calculate the second moment. Mx double prime of t. So I take the derivative again. A negative 2 is going to come down. I'll get a lambda coming from here. The negative and negative reinforce. I get a 2 lambda squared, 1 minus lambda t to the minus 3. I plug in t equals 0, and that gives me a 2 lambda squared. This is the expected value of x squared. So if I now want the variance of x, that's just the expected value of x squared minus the square of the expected value, which is 2 lambda squared minus lambda squared, which is lambda squared. So the standard deviation of x is just lambda. So we've regained all of that calculations from having the moment generating function. That was one way to do the calculation. There is another way to calculate all the moments of this distribution. Anybody know what's the other way? Yes? Well, if we're taking derivatives, that's essentially the same calculation here. There's a way to do it in some sense without doing derivatives, if you recognize this. Cameron, what game were you and I playing that you beat me in this morning? You forget? Oh, good. You don't remember at all? Well, we were playing in my office. You got to say it louder so the students can hear. Okay, we were playing basketball. Does the hint of basketball help you at all? Where have we done basketball in this class? What do we use the basketball to prove? The geometric series formula. Geometric series formula. If the absolute value of r is less than 1, then 1 plus r squared plus r cubed equals 1 over 1 minus r. There is nothing that says you have to read from left to right. You could read it from right to left. If you read it from right to left, or 1 over 1 minus r is 1 plus r squared plus r cubed plus dot dot dot. Why is this a good way to read it? For the exponential, we have the moment generating function of x at t is 1 over 1 minus lambda t. So what do we take r to be? Lambda t. So the series expansion for this is just 1 plus lambda t plus lambda squared t squared plus lambda cubed t cubed. But we know it's equal to 1 plus mu1 of t plus mu2 prime t squared over 2 factorial plus mu3 prime t cubed over 3 factorial. That's the moment generating function. That's its expansion. The only way these series can be the same is if they're the same term by term by term. So this means mu1 has to be lambda. This means mu2 prime has to be 2 lambda squared. So this gives us mu1 equals lambda. This gives us mu2 prime is 2 lambda squared. If we wanted, we would immediately get mu3 prime is 6 lambda cubed. And in fact, you can now pull off all the moments of the exponential. If you think about what we were doing over here, you can see as I keep taking more and more derivatives, I had a negative 2 come down. I have this to a negative 3. I'm going to now have 3 times 2. I should not have written this as 2. How should I have written this? I should have written this as 2 times. I should have written this as 1 lambda. And then this would have been much better to write as 2 times 1 times lambda squared. Yes? Sure, because when you evaluate at t equals 0, if you take 5 derivatives and then set t equal to 0, the only term that survives is the 5 derivatives applied to t to the 5th. If you have t to the 4th, if you take 5 derivatives is enough to kill t to the 4th. If you have t to the 6th and you take 5 derivatives, you're left with the t, which when you take t equals 0 will vanish. So the only term that survives when you take n derivatives is the t to the n term. You get an n factorial coming down, canceling here, and you're left with mu n prime. Okay. So we could have actually seen that those should have been the moments without doing more calculations. You could do this formally through induction, but you can also use the geometric series formula. For those of you who took multivariable calculus, did you ever have to do Taylor series in multiple dimensions? Taylor series of a function of x and y? This is not sounding familiar. I know my students did it. So you have all these formulas involving the mixed partial derivatives, and you have these long, messy formulas. A lot of times, you can actually bypass having to do a 2-variable Taylor series by doing a 1-variable Taylor series. So I will just remind you or introduce you to this important trick. So let's say we want to Taylor expand the sign of x plus y. So one way to Taylor expand this is I evaluate first it at x equals y equals 0, then I take the derivative with respect to x, derivative with respect to y, derivative with respect to x twice, derivative with respect to y twice, derivative with respect to x and y. Oh shoot, do I have to put a factor of 2 in front of that? Is it a 1/2? Which way did things go? Then start worrying about derivatives 3 times and whatever. It becomes a nightmare. Here's the trick. The function only depends on x plus y. So if I look at u equals x plus y, the sign of u is u minus u cubed over 3 factorial plus u to the 5th over 5 factorial. So we get the sign of x plus y is just x plus y, the linear terms, minus x plus y cubed over 3 factorial, the cubic terms, plus x plus y to the 5th over 5 factorial, the quintic terms, minus dot dot dot. And so if I only depend on x plus y, I can create a new variable, expand it in terms of that new variable, and then substitute. If I had the sign of x plus y plus something else, maybe I do those two pieces independently. It would have been a lot painful, a lot harder if I had the sign of x squared. Because if I have the sign of x squared, when I start expanding these quantities, everything would not be of the same degree. Now in that case, this is now really bad. This is a quadratic term, this is a linear term. When I expand this here, I'm going to have a term of degree 6 all the way down to a term of degree 3. So some of these terms are actually lower order than some of the terms from over here. So in a case like that, the algebra can become a lot worse. But you want to know the fast paths through this. And so over here, we could take the derivatives. This is a formal way. It's always going to work. The most important thing is, do you have a method that will get you a solution in a reasonable amount of time? If you do, go for it. I still remember I had a great professor at Yale, Peter Jones. I had 3 classes with him. He would write harsh comments on some of my exams when I needed to hear it. And there was one exam where I had filled up 2 pages on a long, tedious calculation in complex analysis, and then I wrote, there's got to be a better way of doing this. And 4 lines later, there's an answer, because there's an elegant way of looking at it. He wrote in the margin, it's about time you realize this, Steve. And he was absolutely right. On an exam that you're taking in class, he's not going to give you something, I was about maybe a third of the way done with the calculation, that's going to take that long to do. I knew it would work, but it would take too long. There should be a fast, elegant way of doing it. And so you want to get to the point where you can say, okay, I have a method. God forbid if I have to, I can take the derivatives. I can do it that way. I've got a formal way that will work. I have the quadratic formula. I can use the quadratic formula and I can solve it. But is there a way to just step back and look at what's going on, bypass this, and connect this to math I know? If you can do this, if you can start to really see the connections, it'll be a lot better. This is really the same as the geometric series. And so as long as you know the geometric series formula, boom, you get all the moments. That's my goal, is for you to get to the point where you can recognize stuff like that. All right, so the last thing I want to talk about is we're going to be doing something called standardizing random variables. And the idea is we want to compare not apples and oranges, but we want to compare apples and apples. So standardization. And what we'll frequently do is we'll let y equal alpha x plus beta, where alpha and beta are constants. Think Celsius and Fahrenheit. I have a nice linear transformation between 2 scales. And the idea is, if I understand x, I should understand y. If I understand y, I should understand x. But maybe one of them is going to be more convenient. We're going to really use this to get our random variables to have mean 0, variance 1. Okay? And in those situations, then which normal are we converging to? We're converging to the normal, the standard normal. If you look at probability textbooks, and eventually I'll have to do this for my book, you'll find tables of normal probabilities in the back. This is the 21st century. It's all online. I haven't really felt the need to do that yet. But notice they only have tables for one distribution, the normal distribution, mean 0, variance 1. They don't have it for others. Why? You can always standardize your variables. You have seen something like this in your past. The log laws we use the most is the log of the product is the sum of the logs. The log of the quotient is the difference of the logs. Another log law is the change of base. And for many years, have we talked about change of base this semester? This was one of the most important ones. The log of x base b is the log of x base c over the log of of b base c. And the reason this is so important is if you understand logarithms in base c, you understand logarithms in any base. You only need to assemble logarithms in one base. People's jobs used to be calculating log tables or digits of pi. It's boring work. You don't want to do more of this than you have to. This tells you you only need to do it for one. The proof is not so bad. So the proof, let's say the log of x base b equals y. This means x equals b to the y. And now I want to write everything in terms of c. So if I have the log base c of x equals w, that means x equals c to the w. The log base c of b, we'll call that w1, equals w2. That will be b equals c to the w2. Well, if x equals b to the y and b equals c to the w, x equals b to the y equals c to the w2 to the y, which is c to the y w2. Okay. So now, if I take the log of x base c, the log of x base c is the log base c of c to the y w2. Well, the log of c to the yw2 is just yw2. And now y, I have a feeling I might have put in too many things. w2 is the log of c base b. Oh no, and w2 is what I want. All right. I might have made a small algebra mistake here. It's time to go. You can fix the algebra here, but the idea is we express x in terms of all the different things we... Oh, I should have probably gone... No. All right. Doesn't matter. All right. So anyways, the idea is we can standardize. We only have to calculate things one way. That's why we only need one table. All right.